Welcome! Now we're going to look at change of variables in calculating integrals, and in particular change to polar coordinates and possibly some other variable systems. Okay, and then we're going to look at triple integrals before we move on to flux. Occasionally it's easier to calculate a double integral like this over some region using coordinates other than x and y, since the shape of the region R might be better suited to polar coordinates, for example. Now, if you have a circular region, well then it's probably best to calculate your integral in terms of polar coordinates because the integral will be far easier that way. Okay, so to do that we need to introduce the Jacobian matrix. So that's this matrix right here. So suppose x and y are functions of some other letters, u and v. Uppercase F is a vector containing x and y. Okay, and so we let the Jacobian matrix be the 2 by 2 matrix because there are only two variables and two variables in x and y, so it's 2 by 2. But of course it could be bigger if we had more letters. So we have the partial derivative of x with respect to u, the partial derivative of x with respect to v, the partial derivative of y with respect to u, and the partial derivative of y with respect to v. So it looks like this. And then of course you calculate that, and then what you need to do is calculate the determinant of that Jacobian matrix when it goes into changing your variables. All right, so we take this double integral, and so suppose we decide that it's better in terms of the letters u and v, say polar coordinates. Well, then what we do is we replace this with f of x of u and v and y of u and v, but we have to include the determinant of the Jacobian matrix, and then we can make that substitution to integrate with respect to u and v. Okay, R asterisk is the region corresponding to R in the new frame of reference. So essentially the same region, just represented in terms of the new letters u and v. So it follows that we've got the following corollary. In other words, a consequence of this result. So if we have polar coordinates, now remember that points on the circle of radius r and center 0, 0 have points parametrized by r cos theta, comma r sine theta. And this is just because cos squared plus sine squared equals 1. So the x coordinate squared plus the y coordinate squared is r squared times cos squared plus sine squared. So in other words, the sum of the squares of these coordinates is r squared, and then taking square roots, well, we just get r. So it works. All right, and so this is the polar representation of the collection of points on this circle. So if we have an integral over a region, uppercase R, say inside this disk, then we might want to change to polar coordinates. So integrating this function with respect to x and y while changing to polar coordinates, well, we have f of r cos theta, r sine theta, and then we have our Jacobian matrix here, or the determinant of it, which turns out to be just r, and then dr d theta. So let's have a look. So if x is r cos theta, then the derivative of this with respect to r is cos theta. The derivative of x with respect to theta is minus sine theta, or r minus sine theta. Okay, now differentiating y with respect to r gives sine theta. Differentiating y with respect to theta gives r cos theta. And then we just calculate the determinant. So the determinant of this matrix is the product of the diagonal elements minus the product of these off-diagonal elements. So the determinant of the Jacobian matrix is r cos squared theta plus r sine squared theta, because we're subtracting a negative, and so this gives us r. All right, now remember that goes in here, but that is right here. Okay, so let's use this now to calculate the volume of a quarter cylinder of height 1 and radius 1, and we'll do this in a couple of ways. All right, so the first way involves us using the techniques we learned previously. So we've got x going from 0 to 1 in this region here. And then what about the y? So if we have x going from 0 to 1, the y goes from 0 up to this curve, y equals the square root of 1 minus x squared. So expressing this region inside that shaded area, we've got the set of all points x, y such that x is between 0 and 1, and y is between 0 and the square root of 1 minus x squared. Okay, so remember how we set this out. Now we're calculating the volume of this, looks like a slice of cheese, right? But it's a quarter cylinder. So the volume of this quarter cylinder. So the area under the plane, z equals 1, inside this shaded region right here. Okay, so we know our region. Now we set up our integral. It's the integral over r of 1. So that's the z equals 1 dA. And so given this, remember we put the constant on the outside, and then we've got 0 to the square root of 1 minus x squared on the inside. We're integrating 1. Now this goes with y, so we put dy, and this goes with x, so we put dx. Okay, now let's complete this. I'm putting it over here so I can save some space. Now we've got the integral from 0 to 1. Integrating 1 is just y. So from 0 to the square root of 1 minus x squared dy, and that's no, dx, okay, because we've just integrated with respect to y, and this is y equals 0 to y equals square root of 1 minus x squared. So now we got to sub it in. Okay, sub it in and take that difference. So we have an integral from 0 to 1 of the square root of 1 minus x squared minus 0 dx. Okay, so to finish this off, we need substitution. So we say let x be equal to sine of t. Okay, so if we have x equal to sine t and we want to do a substitution here, well then we differentiate. So dx on dt is cos of t, and so then we're going to replace dx with cos t dt in here. Now also 1 minus sine squared is cos squared, so taking the square root gives us just cos. So we've got a cos times another cos. So this is the integral from 0 to 1 in x, but in terms of t, that is the integral from 0 to pi on 2. And you can see that from this angle anyway. That's pi on 2 radians to get to here, from here. Okay, so cos squared t dt. Now this integral gives us pi on 4. Okay, so that's one way. Now another way is to ask yourself, what is the volume of a cylinder? It's pi r squared times the height. Now the height here is 1. So we've got, and the radius of this circle is 1, so pi times 1 squared times 1. So we get pi for the volume of the cylinder, but we have a quarter of it. Okay, and so we'll get pi on 4 for that. Now, there's another way. So let's do this in polar coordinates because that's what we're studying now. So via polar, we've got double integral over r of 1 dA is integral from 0 to pi on 2, 0 to 1. Now, remember, in that substitution, we've got to put the determinant of the Jacobian, and that in this case is r. So we have r, and then we have dr and d theta. Okay, and so this integral is pretty easy. We just have a half r squared and so we get a half here because when we sub in 0, we have 0. So integral from 0 to pi on 2 of 1/2 d theta. And so we've got 1/2 theta from 0 to pi on 2. And so we just have to sub in pi on 2 and sub in 0 and take the difference. So this gives us pi on 4 minus 0, which is pi on 4. Now there's yet another way, which is via volume of revolution. But I don't think we need to do that here. It's convincing enough, and this is the main exercise. So let's leave it at that on that page. Okay, let's look at another example of change of variables. Example 5.7. Consider the region shown in figure 34. This region, so I've got a diamond-shaped region. With change of variables u equals x plus y and v equals x minus y, calculate the volume under the surface z equals x squared plus y squared dA, where r is the region shaded. So here we've got r. Now let's work out where our axes are. This is the x-axis, and then this is the y-axis. Now, what are the boundaries here in terms of x and y? Well, this is the line y equals x. This down here is the line y equals x minus 2. This here is the line y equals minus x. And this here is the line y equals minus x plus 2. Okay, and so we could calculate this integral in x and y coordinates, and that's easy enough to do. But it's even more natural if you shift this and look at it from this frame of reference, where this is the v-axis and this is the u-axis. All right, so in terms of these axes, what is the line y equals minus x plus 2? Okay, so that's the line u is equal to 2. And how do we get that? Well, have a look at this transformation here. When we sub in or replace y with x minus x plus 2, the x's vanish and we just have u equals 2. Okay, similarly, if we replace y with minus x in that expression, we've got u equals 0. Okay, now what about this line and this line? So this y equals x, well, that says v equals 0 from this. And this y equals x minus 2, well, that says v equals x minus x plus 2, so v equals 2. Okay, and so in this frame of reference, it's probably easier to calculate the volume under this surface z equals x squared plus y squared. So I think I've probably got a plot of this. Let's have a look. Here's the diamond-shaped region. And then here is the volume under that surface, x squared plus y squared, within that diamond-shaped region. So what we're doing is we're essentially making a change of coordinates and looking at it from this point of view, so suddenly that diamond becomes a rectangle. But to do that, we need to calculate the Jacobian matrix and take its determinant. Okay, so to begin with, what we need to do this is we need expressions for x and y in terms of u and v. So what we want to do is take these two equations. I better turn this right side. Okay, let's take these two equations and solve for x. So if we do that, we've got u equals x plus y and v equals x minus y. So if we take this and add, so adding, well, the sum of that says that u plus v is 2x. So we get x is equal to 1/2 u plus v. Okay, so we can write that down here. Half u plus v. All right, let's do the same thing for y. Now, to get an expression for y, we want to make the x's vanish in this. So subtracting, we have u minus v is 2y. And so y is 1/2 u minus v. So let's write that here. Okay, next, let's take the Jacobian and its determinant. So we need to differentiate these two partially with respect to u and with respect to v. The partial derivative of x with respect to u is 1/2. Partial derivative of x with respect to v is also 1/2. The partial derivative of y with respect to u is 1/2. And the partial derivative of y with respect to v is minus 1/2. So taking the determinant here gives us minus 1/4 minus 1/4. Now there are two of the quarters there, so we've got minus 1/2. But note, swapping columns or rows, so had we set this out differently, we'd get a different sign. So in what follows, we're going to have a minus sign, so we can interpret that as the need to maybe swap rows or columns, or simply interpret it as positive. Okay, now, so here at the top of this page, we have this diagram. So we're looking at it something like this, and we're calculating the volume under this in terms of u and v coordinates. Okay, so this is 0 to 2 and 0 to 2. Now in terms of u and v, we've got 1/4. So x was u plus v. And then y was u minus v. And then we've got to put in the determinant of our Jacobian. So that was minus 1/2. and then du dv. Okay, fantastic. So now we have to calculate this, so expand it, pull a quarter out, collect like terms, and so on. Let's pull the quarter out and expand, and so we have u squared plus 2uv plus v squared plus u squared minus 2uv plus v squared, and then that's all times minus a half, but you know what, we can take that out too and call this minus 1/8 du dv. Okay, so now let's collect like terms. We can see that these two vanish. And so we've got 2u squared plus 2v squared du dv. Okay, so we could make another line and pull the u out and call this minus a quarter integral u squared plus v squared. Now, we may as well just integrate at this point with respect to u. So let's do that. Integrating this with respect to u, we have u to the power of 3 over 3. But let's pull that 2 out in this step. Okay, so having pulled the 2 out and integrating with respect to u, we'd have uv squared there. And that's u goes from 0 to 2. Okay, so next we want to sub in our 2 and our 0 for u. So 2 cubed is 8, so we've got 8/3 plus 2v squared. And then they both have u's, so it's minus 0. I'm just checking to make sure I haven't made any mistakes. Okay, this looks fine to me. So now we need to integrate this with respect to v. So we've got 8/3 v plus 2/3 v cubed, 0 to 2. Okay, it looks like we can pull out a 1/3. Subbing in the 2 for v, we've got, so minus a quarter times a third, brackets. Now putting the 2 in for v, that gives us 16 there. And then we also have a, so 2/3, 2 to the power of 3 is 8 times another 2 gives us 16. And then we, of course, subtract 0, but we don't need to write that. So 32 over 12. Okay, now 32 is 8 times 4. So if we cancel a 4, do we have minus 8 over 3? I think so. Okay, and so let's just double check. So 32 divided by 4 is 8. So 8 over 3, yep, minus sign. But interpret this volume as plus 8 over 3, right? Because obviously we would need to do a row swap in our Jacobian or something like that. Now, there's another way to do this. If we never change coordinates, well then we would be calculating integral from 0 to 1, x goes from y to 2 minus y of x squared plus y squared dx dy, and adding that to, now all we're doing here is we're slicing this down the middle and taking this as the sum of two integrals. So the other way, or the other part of it, would be from -1 to 0, integral from minus y to y plus 2, x squared plus y squared dx dy. And so when you calculate this integral here, you will get 8/3. Okay, so the volume under this surface within that region is 8/3 units. All right, let's move on to the next topic, which is triple integrals. And so the regions I've set out are fairly simple in the exercises that we'll do. So we'll consider 2 examples and then some important results on triple integrals. But for this session, we'll just do the 2 examples. Okay, let B be the set of all triples x, y, z such that x is between 0 and 2, y is between -2 and 3, and z is between 0 and 1. Okay, so we've got our z-axis, and then this looks like it's, let's see, what is this? This looks like the y. Is that right? Coming out this way. No. Maybe this is, you know what, I can't tell where the axes are at this point. So we'll just rely on this, okay? So this says calculate the triple integral over the region B of x cubed y z squared. So we've got, this is our region B shown there, but then we've got to calculate this integral within that region. And so a volume interpretation is not quite accurate, you see. All right, let's move on and calculate that. So leave that one there for now. So we write this as the integral from -2 to 3, integral 0 to 2, integral 0 to 1 of x cubed y z squared dz dx dy. Okay, now this is a fairly easy integral. So integrating this with respect to z gives us 1/3 x cubed y z cubed. And so that's z equals 0 to z equals 1. Okay, subbing in the 1 and the 0 for z, we have 1/3 x cubed y, and then minus 0. Okay, now moving on to the integral with respect to x. So we have an x to the 4th. Dividing by 4 gives us 1/12 x to the 4th y, as x goes from 0 to 2. And now we've got to sub in x is 2 and x is 0, take a difference. So 2 to the power of 4 is 16. So 16/12. And then times y. Okay, so 16/12 is 4/3. So integrating that with respect to y, we've got y squared. Now half of 4/3 is 2/3. And all that remains here is to sub in 3 and 2 and minus 2 and take a difference. So 3 squared is 9. 9 divided by 3 is 3, so that's 6 minus, now minus 2 squared is 4, so we have 8/3. So 6 is 18/3, and so we get 10/3. Okay. So now we have a more interesting region here. So let's discuss the region. So it looks to me like x comes out this way, y out this way, and then z this way. And so we've got a boundary here on the xy plane. That's the boundary, y equals x. And then this boundary here is the boundary of a plane. So that's the boundary. Z is equal to x minus y. And so we are calculating the triple integral of 4xy within this region. Okay, and so let's set this integral up. So 0 to 3 for x. So then that goes with a dx out here. And then next we put 0 to x. So that's for the y. That goes with a dy. And then 0 to x minus y, going with a dz. Okay, what are we integrating? 4xy. Okay, so this is somewhat easy to integrate. Also, so we just have 4xyz as z goes from 0 to x minus y. Okay, now let's sub those values in. And then probably helps to expand that first before you integrate it. Okay, so now let's integrate this with respect to y. And so we're adding 1 to that exponent of y, dividing by 2. So we have 2x squared y squared minus 4/3 xy cubed. Y goes from 0 to x. So now we need to sub in y as x. So we've got 2x to the 4th minus 4/3 x to the 4th, and then subtract 0. Okay, we're just about done with this. So these are like terms. So 2 minus 4/3 is 6 minus 4 over 3, which is 2/3. And so integrating that means increasing the exponent by 1 and dividing by the new exponent. So we have 2/3 times 1/5 is 2 over 15, x to the 5th. Okay, and then we sub these values in. So let's see, 3 to the 5th is 3 to the 4th times 3, so we can cancel a 3 in the 15 and in here. And so we'll have 2 times 3 to the 4th over 3. Oh, sorry, over 5. That's right. So that is equal to 81 times 2 over 5, which is 162 over 5 units. Okay, let's do a little bit of physics now. So we're going to look at flux and Gauss's divergence theorem. And so this is surface integrals. So the appropriate section is surface integrals over fields. and that's in Stewart. I use the 7th edition. And this, in the 7th edition, it's around chapter 16, page 1140. Okay, and I have to also say that this is somewhat premature being here in the end of chapter 5, because what you really need to do is have a look at the beginning of section 6 and in fact see a few line integrals. So you might feel comfortable going through chapter 6 first before you do this, or at least a little bit of it, so you sort of get the picture for what's going on here. All right, so to introduce Gauss's divergence theorem, and again, this is sort of motivation for the need for div, for example. We introduce the concept of flux. This quantifies a vector field passing through a curve or a surface. In the plane, the net outward flux of the vector field f is given by the line integral. So this is a line integral, and it would help if you already knew what a line integral was. So I'd encourage you to go and have a look through section 6. You don't have to go very deeply into it. Just have a look at what a line integral is, and so maybe you understand this a little bit better. So this is a line integral. You see the C down the bottom. So it's described in terms of some curve. And so section 6, or chapter 6, in particular, I think towards the middle or end of chapter 6, but parameterization is in the beginning of it. We've already done a few examples of parameterization of lines and even planes, so it shouldn't be terribly foreign. Okay, so it's given by this, where n is normal to the curve C pointing perpendicular from the curve or surface. Now this is a toy example of flux, because when you calculate flux, you've got a sheet or a surface and you've got a vector field passing through that, right? For example, an electric field is a three-dimensional vector field. So you've got 3 letters x, y, and z, and it passes through some surface. So you might calculate the flux, or the quantity of electric field passing through some particular surface. Now have a look at figure 38, but I've got a better version on the left-hand side of the screen. So let's have a look at that, because what I want to show you are 3 vectors. So here I've got the origin over here on the left. It's the tail end of the vector, and the head of the vector touches a point of this curve. So as I move t, you can see that vector, the red vector r, continues to touch a point of the curve as we go along. Okay, so that curve, I have parameterized it. So let's have a look at the parameterization. We'll write that down here. C is the curve consisting of the vector r of t, which is equal to 2t plus 4 minus t squared plus 2. Okay, now there is a curve here in the xy plane as well, right? And this is as t goes from 0 to 2 in this parameterization of this little curve segment. All right, but let's, while we're at it, find what the curve is in xy coordinates. So this is x, this is y, so I can take x equal to 2t plus 4 solve for t and then sub it in here. So let's go ahead and do that. So this says t equals x minus 4 all over 2. Now if we square that and sub it in there, then we have y is equal to minus x minus 4 all over 2 squared and then plus 2. So let's expand this so we can see that this is a quadratic relationship here. So we've got minus a quarter outside of x squared minus 8x plus 16 and then plus 2. Okay, and so if I expand that minus a quarter in, minus a quarter times 16 is minus 4. Minus 4 plus 2 is minus 2. So we have minus a quarter x squared plus 2x minus 2, I think we said, right? Okay, so here is the xy relationship for that little curve there. And so what this is it is a parameterization over the letter t of this curve. But it's not just the curve, it's a segment of the curve. So from t equals 0 to t equals 2. All right, so there's a little crash course on parameterization of curves, but of course there's a lot more to it. Okay, so now we've got r. Let's take the derivative of that. So r dash of t. So differentiating this vector with respect to t, we have 2, and then we have minus 2t. All right, now what about a vector perpendicular to this? So that would be n, but I actually want a vector perpendicular to that, which is a unit vector. So n hat as a function of t is equal to, now what I do is I swap the two of these and then change the sign of one of them, but I want to scale it as well. Remember, I'm calculating a unit vector, so I want the resulting vector to have norm 1. So if I put t comma 1 and calculate the norm of this, well, it's the square root of t squared plus 1, so I want to divide that away so that the result has norm 1. Okay, so now I have a unit vector that is perpendicular to this one. So it's perpendicular to r dash of t for any given value of t. All right, so let's go back to this diagram on the left of my screen, I guess on your screen too. So remember, the red one is the vector r, so this one. The black one down here, this black arrow, probably want to take the t value down so that you can see this a little better. So the black arrow here is r dash. In this case, it depends on t, you see. Okay, now the green arrow is that unit normal vector, so it's perpendicular to r dash. Right, so meaning that it's perpendicular to the edge of that curve at that point right here, for example, right? And then r dash is tangent to this curve at that given point. Okay, so we've got 3 vectors here of interest. All right, now another thing to discuss here is that what is ds? So ds is an infinitesimal of surface, but in this case it's not a surface, it's a curve. So it's a little piece of this. So again, have a look in chapter 6, you'll see a diagram and a discussion of ds. Okay, so let's go ahead and have a look at the next page. Here we have a simple example. Calculate the net outward flux of the vector field F equal to x plus y comma minus x squared minus y squared, and it's shown there with all these arrows. And incidentally, in this one, we also have a vector field. It's all these little blue arrows, or blue arrows you see there. Okay, so the question is how much flux, or a quantification of the number of arrows, or the strength of the arrows going through that, for example, all right? And so similarly here, so you would expect in this case that might be fairly small, right? Because near this edge, the arrows seem to be almost parallel. Okay, so let's have a look at this. So take, for example, some given point here. Now, since this is a line, all of the unit normal vectors are equal in this case. So something like this, right? Perpendicular to that curve. Now, a tangent, so r dash would be parallel, and r itself would go from, I guess the origin's here, right? So from the origin to the point, so this is r of t, and then r dash of t is tangent to that curve. In this case, it's a line. The unit vector n hat is perpendicular to r dash, and hence perpendicular to that curve at a given point. Okay, great. Except in this case, I think r dash goes the other way according to my notes. So r dash goes this way. All right, so let's have a look at this. So we've got a line, y equals minus x plus 1, just that line there. So let's parameterize this. So how do we do this? Well, let's look at a description of the points on this line. So if we take, let's see, we want to say parameterize this in terms of the letter y. So the line y equals minus x plus 1 has points described by, now if I just choose the y coordinate as y for now, well then what's the x coordinate? It's minus x plus 1. Right, but if I write x in terms of y, and we can do that just by taking this over and this over, so x is equal to minus y plus 1. So I can write here 1 minus y being the same thing. All right, so this describes a collection of points on this line. But now if I want to talk about a segment of that line, well, I can let that y go between something and something. All right, so now describing that in terms of a different letter, say t. So we've got c being the set of all pairs, 1 minus t, comma t, such that t is a real number and t is between 0 and 1. Right, so now notice, so when t is equal to 0, we get the point 1, 0. Okay, and that's down here, 1, comma 0. So we're starting here with the values of t, and then we finish here. And this is the point 0, 1. Okay, so when t is equal to 1, we get the point 0, 1. So we start here, we finish here. Okay, now let's calculate. So this is r. R of t is equal to 1 minus t, comma t. Now let's calculate what r dash is. So r dash of t, just taking the derivative of this with respect to t, we have minus 1, comma 1. All right, so to the left 1 unit and up 1 unit, so like this. So going this way. Okay, now what about n, so it's perpendicular to this, so I swap those components, and I put a minus sign on one of them, and then I divide by its norm. So n hat is equal to 1 on root 2, 1 comma 1. Okay, so I've got those three things, so I can now calculate the flux. And incidentally, I can calculate that using a cross product as well. So let's go ahead and do that just to show you. So we can calculate the cross product. Now this is a unit vector that is parallel to the curve at some given point where t gives the point. So it's given by this, right? And I can see I should have divided by the norm. So 1 on root 2. Okay, so that this has unit length, unit magnitude. All right, so now let's calculate the cross product so you can see that you get this of minus 1, 1 cross k, but actually I need to add another component to make this 3D. So I'll put a 0 there in the third component, and we'll cross this with the k vector, or k hat, which is 0, 0, 1. So we set this out as a determinant, I hat, j hat, k hat. Then we have minus 1 on root 2, 1 on root 2, and 0, and then in the bottom row 0, 0, 1. Okay, so in the cross product, we cross out the column and the row that the I hat is in, and we have 1 on root 2 times I hat. And then we cross out the column and the row that the j hat is in, so then that's minus minus, because we put a minus in front of that because it comes second. J hat, and then similarly cross out the column and the row that the k hat is in, take this 2 by 2 determinant, and we get 0. So 0 k hat. Okay, now there are two minus signs there, so we can represent this as a vector without the I hat and j hat, and just call this 1 on root 2, 1 comma 1. Okay, and you can see that that's the same as this. Okay, so we've got those three things that we need, r, r dash, and n hat. So now let's go and calculate the flux, or the quantity of vector field passing through that curve. And so it's given by this. Now remember, C is this. All right, C appears down there. So we've got an integral over C. Now F was x plus y minus x squared minus y squared. And then that's a dot product. So we're dotting that with the unit vector n hat. And then we have ds. Okay, now looking forward to the info on line integrals. All right, so this is referring to chapter 6. I'll put a little box around this information because this is something from future studies. Okay, so we have integral over C, or the line integral of f of xy ds is an integral from a to b f x of t y of t times the norm of r dash of t dt. Okay, and you can find this in Stewart, 7th edition. Of course, it's in the 8th edition too. That's page 1092, and also in notes, chapter 6, Section 6.4. Okay, so we're going to make this change next after we take our dot product. So then we've got an integral from t equals 0 to 1. Now what we're doing here is we're replacing x with the parameterized form. So x would be 1 minus t, then plus y, that's t. Then we have minus x squared, that's 1 minus t all squared, and minus t squared. We're dotting this with 1 on root 2, 1 comma 1. And then we need the norm of our dash according to this. dt. Okay, so now we just take the dot product. So this times this, added to this times this. So there will be a 1 on root 2 in both of those. So we want to pull that out the front. Okay, so then we have, now here we've got t minus t, which vanishes. So that's just 1 times 1 is 1. And then the expansion of this one maybe is a better way to represent that. So let's expand this. So in the expansion, we've got minus 1, and then minus 2t, but then multiplied by minus 1. So that's plus 2t. And then minus t squared, but then there's another minus t squared, so minus 2t squared. Okay, so that's the expansion of that times 1 gives us this. And then the norm of our dash was just root 2. Okay, so or was it? Hang on, let's find this. No, we've got yeah, that's right. The norm of our dash is root 2. So no, this is not right here. Okay, so go back and get rid of that 1 on root 2 there. Because that's t, right? That's the unit tangent vector. Okay, so it's just minus 1, 1. So yes, the norm is root 2. Okay, so these two root 2's can cancel one another. And these ones vanish, so we've got the integral from 0 to 1, 2t minus 2t squared dt. Okay, now this is fairly easy to complete. So we have t squared, and then we have minus 2/3 t cubed from 0 to 1. We sub in t is 1 and sub in t is 0 and take a difference. So we have 1 minus 2/3, and so that's 1/3. Okay, so the flux there is 1/3 units, whatever those units are. Presumably that's in the appropriate scientific units, or SI units, right? Okay, Gauss's divergence theorem. Assume f of x, y, and z is a vector field that's continuously differentiable in the closed region V, a subset or equal to 3 space. Let n be a unit normal vector to the surface S, that is the boundary of V. Then the flux of f through the surface is given by this integral about that surface of f dot n ds, but we can trade that in for a triple integral involving div. Now you remember div from chapter 4, dv. If there's a net flow out of the closed surface S, then integral flux is positive. If there's a net flow into the closed surface, then the flux is negative. Okay, so let's have a look at this example. Kind of a nice picture. I'll leave that accessible there. All right, so use Gauss's divergence theorem, and I'll just display this here as well, to calculate the flux of the vector field 3x, 4y, 5z over the surface S. So this in here, that ball is the surface. Here's our vector field, and we're calculating how much field passes through that ball. Sphere of radius 2, this is our surface, and centered about the origin, see figure 40. Okay. So here we have a parameterization of the inside of the sphere of radius 2. So r goes from 0 to 2, that's inside this. Phi goes from 0 to pi, and theta goes from 0 to 2 pi. Okay, so let's go ahead and calculate our flux now. So by Gauss's divergence theorem, we can trade this integral over that ball in for a triple integral over V div f dv. Okay, so let's calculate div f here. So div f is div of the vector 3x, 4y, 5z. And remember, that's the partial derivative with respect to x of 3x plus partial with respect to y of 4y, and then with respect to z of 5z, and this is 3 plus 4 plus 5, so we've got 9 and 3 is 12. Okay, so div of f is 12. So this becomes triple integral over v of 12 dv. Okay, so at this point we want to use polar coordinates. Now reflecting back on this, so we have theta goes from 0 to 2 pi. So we'll put theta, d theta on the end there. Okay, then we have phi from 0 to pi. So phi goes next on the inside of that. And then we have, what are we missing here? R. Okay, so R goes from 0 to 2. And then we need our Jacobian for that change of variables. Now this is in the appendix on the next page. So I'll just point you to that first. Right, so these are our polar coordinates in 3D, where let's just point out, okay, this is really tiny, so that's an x-axis, y, and z, and then down here we've got theta, and this angle here would be phi. I think. Okay, and so when we take the Jacobian matrix, we have this, and then the determinant gives us this, which then simplifies as r squared sine of phi. All right, and so what we need to do then is put r squared sine of phi in here as the determinant of our Jacobian matrix. And then what we're integrating is 12 times that. Okay, fantastic. So now, to finish this off, we've just got to perform the integral. So integrating this partially with respect to r, so we raise that by 1, so r cubed, divide by the new exponent, so 12 over 3 is 4 r cubed, as r goes from 0 to 2, and then we have d phi d theta. Okay, we've got to sub this in. So 4 times 8 is 32. Oh, and have I included, I haven't included sine phi, have I? Okay. So then we need 32 sine phi d theta. All right, so next we've got to integrate sine of phi with respect to phi. So we've got minus cos. Let's pull the 32 out. Actually, let's pull a minus 32 out. So then we just have cos of phi, 0 to pi d theta. Okay, and so then next, minus 32, integral from 0 to 2 pi. So here we've got cos of pi minus cos of 0. All right, now cos of pi, think about this. It's all the way over here, pi radians. So that brings you to minus 1. Okay, now cos of 0 is 1. So we've got minus 1, minus 1. Okay, this is minus 2. So bringing this all out, minus 2 times minus 32 is 64. And so we've got 64 times theta from 0 to 2 pi. And so subbing that in, we've got 128 pi. Okay, so that would be the flux through this sphere.